Hello again, and welcome back to my computer vision series. My name is Mac. If you are new to my channel, here is what was going on so far. We started with the task of image recognition, just one of the many areas within computer vision. We have built a simple neural network using PyTorch to classify digits. Our next big challenge is the ImageNet dataset. A lot of data, high-resolution images, and big models. We're not quite there yet. In the previous videos, we talked about the tools we'll need for such a model, that is convolutions, parameter initialization, activation functions, and optimizers. In this video, we are finishing our toolbox with residual connections, batch normalization, and Kaiming Initialization. Let's go. Here is an interesting illustration of how it feels to do deep learning sometimes. You start with something simple, like a linear model, and it works. Then you add a couple of more layers, and it works even better. But eventually, as you add more and more on top of that, the whole system becomes unstable, and eventually it just breaks down, and you can't seem to be able to train anything. The tools we discussed today, residual connections, batch normalization, and Kaiming Initialization, helps us make sure that we maintain the stability of the entire system as we add more layers. And this is the key to unlock really deep models that can solve really challenging tasks. First, let's discuss why do we even need residual connections? What is the problem we're trying to solve? We've talked about this problem before. It was widely discussed in papers. For example, in this one from Xavier Glorot and Yosha Benjo in 2010. I have a really in-depth explanation about this paper in one of my previous videos. And so what it basically says is, if we have a quite deep neural network, layer after layer after layer after layer, obviously the transformation that happens to the values after each layer can be quite complex. But if we look at the range of values that we get, it's also sometimes called variance. So the sort of range that the actual values will lie in. This range gets multiplied by a certain multiplying factor. And for forward prop, that factor is computed by taking parameter variance during initialization and the size of the layer, of the current layer. And then during backward prop, as we go from the output towards the input, we have a similar multiplying factor for the range of the gradients, but now it's MF prime. And MF prime is calculated as, again, parameter variance times the size of the next layer, because now we are going from the output towards the input. And this is a conflict because layers will not be the same, at least because we have to start with a really big image and then somehow end up with predictions for 1,000 classes, for example. So the shape of the input and the output will always be different. So the sizes of the layers will be different as well. And because of that, we can never precisely satisfy both of these conditions. And it's not such a big problem if the network is not too big. So if you had a multiplying factor of 0.9, for example, then if we take it to 20th power, that's still 0.12. So it's still fine. But then if you have a really deep network, like 150 layers, even with such a gentle multiplying factor, you would end up with a range that is basically zero, which means that your gradients are not really changing. Your gradients are basically zero for all the values that you get, which is really unfortunate because this factor gets applied for every time you step backwards during backward prop, meaning that the gradients will be fine for last layers, but then as you start to reach the initial layers, the gradients will be zero. And so what this means in training is that you have started with just random parameters for layers, and now your last layers will train just fine, and your first layers will be still random. So whatever it is that you pass there will be close to random as well. So it's quite useless to have good final layers if the data passes through a bunch of random layers, and anything good that you could get out of the data is still gone by this time. So we really need these initial layers the most because they are closer to the ground truth, to the data that we have, but we cannot train them. And the solution was proposed by a group of researchers also working on solving the ImageNet challenge in 2015. And they proposed to just add some skip connections, which is really brilliant if you think about it. If you think about vanishing gradients problem as, every time you pass through extra layer during backprop, you lose a little bit of your gradient. So now let's just add skip connections to let the gradient flow along this skip connection as well as through the layers. So it will not vanish. It will just always have this direct path. So it will work. And in code, it looks quite simple. So imagine that we have this block here in PyTorch. So this one takes the input, applies convolution, applies activation function, and then some pooling. And now instead of outputting this value from the pooling, we also just add the input tensor as well. So there is no special residual block implemented in PyTorch. There is nothing special we need in implementation. We just use this pre-existing sum operation that already does everything that we need. And it's not adding any extra complexity to the computation. It's not adding any trainable parameters. So implementation is really lightweight for residual blocks. And this is all there is to it, honestly. There's nothing more to residuals that you need to know. But I also provide a couple of explanations about why that works and why that should work. So first motivation is this. So let's imagine that we try to plot the quality of the model, the training error, with respect to the number of layers. And we would expect it to go down because the model becomes more complex. It should be able to approximate more complex dependencies. At the very least, we should expect it to plateau somewhere, saying that, this is the best we can do, but then adding new layers will not change anything. We don't expect it to become worse because if you imagine that we had a model that is somewhere here in the optimal point, if we add a new layer, in order for the model to remain at least as good, so to sort of become a horizontal line, this layer just needs to learn what's called identity transform, which is just taking the input and just copying it to the output without modifying it in any way. But for the reasons we described before, this doesn't happen. And this extra layer is not able to effectively learn this identity transform. So what residuals do, they basically add this identity transform explicitly. They say that we added this layer, we added the residual connection, which makes sure that the network is at least as good as the previous one because there is this direct connection. And then this layer might add some complexity on top of that if it is needed. And here is another way to look at that. So you can imagine that a bunch of skip connections that skipped all the layers, they basically form a direct line from the input to the output, maybe passing through some linear transformation. And it actually makes sense to have this direct connection to try to predict the values that you need, to try to explain the data in the simplest terms first, to find simple rules that will explain most of the variance in the data, and then to add more complexity, to add more layers, to fix the problems that we had with this direct prediction. So instead of trying to build a complex rule from the first step, instead of trying to come up with a rule that will be complex and will explain everything, we first try to explain what is happening with simple rules, and then we add a bit of complexity on top of that to simply explain the difference, explain the error. And this is another way to look at what residuals are doing. And the result of that is really well demonstrated by two papers by the same authors. So in 2015, this group of authors published a paper about Kaiming Initialization, and this was in February. And they managed to achieve 7% error rate with a model with about 20 layers. And they reported that adding more layers on top of that is not really useful. It degrades the model. And then the same group of authors came up with the idea of residuals. And in December, same year, they managed to train a model with 152 layers and achieve much better error rate. So this basically speaks for itself. So and this model won the competition that year. And nowadays, residuals are used in all models you can think of. So ConvNet, transformers, LLMs, all of them are based on residuals, among other things. Now let's move on to batch normalization. So first of all, I'll explain what is normalization by itself. It actually comes from data analysis, from statistics. A quick explanation would look like this. So imagine that we have a histogram of human height, for example. So average height would be around 160 centimeters, but then sometimes we'll get people who are 180 centimeters or even more, and sometimes we get a bit shorter people, and so on. And then let's compare that to histogram of human IQ, for example. Now, the shape of this histogram looks almost the same, but the actual numbers are, of course, different. Even the units of measurement are different. So to normalize this, what we can do is we can calculate the mean and the variance, the standard deviation of this set of points, basically, of this sample. And then normalize every value by subtracting the mean and dividing by standard deviation. So since mean and standard deviation for this entire data set, as we would call it, is just one number, so this adds basically a simple linear transformation that does not change any dependencies within the data. It just scales all the data points proportionally. But now this looks really neat. So it's a normalized normal distribution curve. So the mean is at 0, the standard deviation is at 1, and we can compare very, very different data sets this way. So we can now compare histogram of human height to histogram of human IQ. For example, to answer the question, are you as smart as you are tall? That will be really important for input data for our network. So for example, if you remember how the tubical activation function looks like, it has this special point around 0. So it works really well if all the data that you have, all the inputs to this activation function are around 0 as well. So they ideally should have 0 mean. So some of the values will be negative, some of the values will be positive. Then rectified linear unit acts as it should. So it will have this nonlinearity only if some of the points are actually negative. But then if you just take a typical picture represented in pixels, and the value of pixel is from 0 to 255, for example, then this is way off. This is not definitely the 0 mean. And so if you take this unnormalized picture as an input, then you pass it through some layer, which usually initialized using 0 mean random initialization. And then you pass that to rectified linear units. All your points will be somewhere here to the right, far away from the actual nonlinearity point here, which might prevent this function to work as it was intended to, at least in the beginning of the training. But you can fix that with just normalization. So you can go over your data set once before the training. You can calculate the mean, the standard deviation, and then normalize the values. And this transformation does not change the actual picture. So the difference between pixels will still be the same. We can still recognize patterns, images from this picture exactly the same way, but now just the range of the input data is fixed. And this is what we actually should do when we train real models. Apart from normalizing model input, we might also want to normalize inputs to individual layers. And that might help with convergence, because if we look at this layer here, for example, we can think of it as an independent component that receives some inputs, and these inputs will have some distribution. And so during a step of the batch gradient descent, this layer will try to adjust to this distribution of parameters. But then what will happen in reality is that on the next step, the previous layer has changed, and so this layer has to adjust all over again. And that is just taking a lot of time. So we might expect to improve the speed of training if we could insert this normalization step somehow. But then the problem is, when we did normalization, we took a certain value, a certain coordinate in the output of the layer. We subtracted the mean and divided that by standard deviation. And the mean is actually just some sort of aggregation statistic over a certain sample. It can be the entire data set, it can be something else. But what should we take as this sample here? What should be the N here? This is one problem that we need to solve. Another problem is that if we insert this normalization step somewhere here, this becomes a part of our computational graph. So when we do backprop, we will need to know the gradients of this computation here to be able to compute all the partial derivatives and to do backprop through this node here. So it was not always obvious on how to exactly do that. So one attempt at this was to just take the entire data set as this sample, but it turned out to be not working really well, because after every gradient step, you keep updating parameters of the previous layers, so their distribution of the output changes, and you can't really afford to go over the entire data set and recalculating the statistics after every batch, because a batch is only just 64 images, for example, and you cannot look over the entire data set with 1 million of images after every batch of 64 images. That will just take a lot of time. And so what batch normalization does is simple. It says that let's look at the current batch as we do the stochastic gradient descent, and just use the statistics from the current batch as our value. So to calculate the mean, we actually iterate over all the values for this specific coordinate across the batch. And we calculate the average, then we calculate the variance, and then we do the value normalization by subtracting the mean and dividing by something like standard deviation. But here we also have this epsilon parameter, which is just a small value needed for computational stability. This thing is differentiable. So now it depends on all the values that we have got in the batch. But since we are calculating the loss for the entire batch at once, since we are doing the backprop for this batch, we are able to compute the partial derivatives of the loss function with respect to all these inputs, all the parameters here. So this formula here, this statistic also takes part in this gradient computation, and we know how to do that. In addition to that, apart from normalization, we also want to do scaling, and we do that because we don't really want to limit the prediction of our network to a small interval, because we might need to represent something that is outside of this interval. So imagine a network that predicts some numbers that can be 100 or higher. if the network is artificially scaled to output something within the range of -1 to 1, it will just never be able to predict big numbers. So to keep that representation ability of the network, we also add this scale and shift implicitly into our batch normalization computation by just multiplying the value that we got after the normalization by a certain parameter gamma and adding this certain bias beta, where these two parameters are learnable. So we start with some initialization for them, but then they are being learned as we do the stochastic gradient descent to actually represent what we want. And this is just one parameter per layer. So if these means and variances were computed individually for each coordinate from the layer output, these two parameters here are just common for the entire layer, which adds just a little bit of complexity to our training algorithm. Because for the layer that might have a million parameters, we only have two extra parameters that we need to train. Another important detail about this is that the statistic, the mean and the variance, now depend on the entire batch, which means that after we randomly reshuffle all the images, this particular image might get a different prediction. And this is not something we want during inference, during validation, because during validation, we want the result to be deterministic, not dependent on shuffling of the data or what other images got into the batch. So when we do inference step, when we do prediction from the model during the validation phase, we replace these estimated mean and variance from the sample with just statistics calculated over the entire data set that will be fixed forever after the network is trained. And this sort of the fact that these statistics are different from batch to batch also add another interesting property to our batch norm layer, that is basically regularization. So we've talked about regularization before in some of the previous videos, but basically regularization is a way of limiting the predictive capacity of the model just a little bit to prevent it from remembering specific examples in the data, thus hurting the train loss a little bit, but improving the generalizability of the model. And there is an interesting paper in 2020 that actually proposed the momentum batch normalization that we'll talk about on the next slide, that also studied a bit deeper this regularization effect of the batch norm. And here is an interesting illustration from that paper. So the authors try to project the activation functions from many, many neurons into the two-dimensional space, and then plot the curve that is basically dividing one class from the other in this projection. And so the colors of the dots correspond to classes, and the dots themselves correspond to specific examples. And so you can see here that the curve here, it's sort of bended a little bit inward because of the way cross entropy loss works, basically. Cross entropy tries to minimize the distance between this dividing curve and the points, to maximize, to push the curve as far back as it can. And so in this particular case, having just a bunch of points around this ends up giving us this weird curve that probably is not that generalizable, because we could have a blue point somewhere here, but because we have only a bunch of points, the network came up with this really overcomplicated rule that probably will only hurt on the test set. But if we add more noise, if we sort of blur these points a little bit, that sort of by itself already makes this separation curve a bit smoother, which is exactly what we want. We want slightly less memorization ability, slightly less performance on the training test, or on the training data, but this will be more generalizable. This will probably perform better on the test set. But then, of course, if you add too much noise, then the points start to blur too much and you start mislabeling examples. So there's a limit to everything. And so there's a problem with this, with batch norm, because the noise that effectively gets added from this statistic estimation that happens on a small batch, the noise depends on the size of the batch itself. And this is not good because we might want to change the batch size for technical reasons, for example. For example, we are training a big model and it doesn't fit in our GPU memory. So we want to decrease the batch size to make it fit. And what the authors suggest is to add the momentum, which is like the historical average over several previous steps of the mean and the variance that is controlled by this parameter lambda here. So you can imagine if that lambda is something that is in 0 to 1 interval. And so if lambda is something like 0.9, that would mean that we multiply current momentum by 0.9, and then we add the new mean that we got on our newer batch with the coefficient of 0.1. And so this will sort of keep something like 10 last batches in this running average, making sure that the noise depends less on the batch size and stays constant throughout the training. And in practice, since 2020, this did become the industry standard for batch norm. So it's basically default option when we do batch norm. Finally, let's talk about Kaiming initialization. So from the first slide, we have described this picture of how variances of the values get multiplied by certain parameters when doing the forward prop, and then the gradients get multiplied by a slightly modified multiplier when doing the back prop. And this different size here, the size of current layer and the size of the next layer, leads to a conflict that cannot be resolved completely in the way we want to initialize our parameters. And so there is one commonly used initialization called Xavier initialization. Once again, I have a video about that in detail. And it proposes just this simple compromise. So we set the parameter variance as 2 divided by sum of the size of the current layer plus the size of the next layer as a compromise between forward and backward prop. However, the paper itself, the math that is done there, does not take the activation function into account. So it's saying that either there's no activation function or that the activation function in the linear mode where the gradient is equal to 1 exactly. And so Kaiming initialization aims to fix that. So it takes a more closer look at what will happen to the variance if we have activation function. This activation function might have non-zero mean like a rectified linear unit does. And it computes basically the extra parameter called gain that depends on the actual activation function used after this specific layer. And then we plug that gain directly into parameter initialization. They also argue that it doesn't really make sense to have this compromise between next layer and current layer size, which is just choose, and the difference either way is not so big. So they choose the size of the next layer as this parameter for the variance. And this mode is sometimes called fan out. But sometimes we also see the fan in initialization that uses just the size of the current layer. And for rectified linear unit, this gain is just the square root of 2. But in PyTorch, we have functions to just calculate the gains for most of the known activation functions that you can just specify as the number for initialization. In reality, though, as I've mentioned, the Kaiming initialization was proposed in February 2015, where they did say that it helps a little bit, maybe 0.1, 0.2% in terms of model quality, and it helps speed up the training just a little bit as compared to just severe initialization. But the same group of authors came up with this much stronger idea of residual connections in December the same year, which practically made initialization much less important. So now you wouldn't probably notice the difference. Having batch norm and having residual connections, the actual initialization does not change much. But it's still nice to know that this exists, and you would see it in the code sometimes, so it's good to know. So this concludes today's video. Once again, we have gone through what is residual connections, what is batch normalization, and what is Kaiming initialization. And in the next video, we are finally putting all of that into practice. So we will get the actual ImageNet dataset, the big dataset that was hosting a challenge for a few years back in 2015, 16, and 17. We will train our own model, trying to do that on our own computer, not depending on anyone like weight, initialization that might be censored, for example, or that might get deleted at some point. We'll do all of that from scratch. We'll see how much more complexity the actual thing has, as opposed to just the set of simple concepts that we have gone through now. So in practice, everything is a bit more complex. We'll go through that. So I hope to see you there. See you soon.